Howdy, it's Boolean Maths here. Today we're going to be talking about rational functions. Specifically, we're going to be talking about vertical asymptotes and holes. I'd like to make this video as short as possible. I really want to focus just on the how behind finding vertical asymptotes and holes for a rational function. The why behind that, I mean, I'd love to explain that. There is another video that I did post that gives a lot of detail about limits and like exactly what's happening, the definition of a vertical asymptote, the definition of a hole, what that means in terms of limits and discontinuity. We're not going to do that right now. We're just going to focus on just how to look at a function and determine what the vertical asymptotes are and what the holes would be, and so on and so forth. So let's get going. All right. Okay, so we're going to look at this example. And yeah, we have three things that we want to look at when we're trying to determine vertical asymptotes and or holes. First, you want to just take the rational function as you see over there. That's function g of x. And we're going to factor the numerator and the denominator. And that's all you're going to do. Don't simplify anything, just factor. So let's do it. So the numerator would be x looks like numbers multiply to be 8 that add to be or negative 8 that would add to be negative 2. I'm gonna go with 4 and 2. We need that 2 to be negative, and so we'll make the bigger number negative, and yeah, sure enough, it works. However you factor, just get it factored. And this is the difference of two squares, so I believe we're all pretty familiar with that. All right, so then we should probably rewrite this function in its factored form. X plus 2 minus 3, x plus 3. Great. Next, we have to state the domain. So we'll just say capital D, and I'm going to use something called set builder notation. So we know that x can be all real numbers except x is not allowed to be negative 3 and 3. Now the reason I'm using set builder notation instead of interval notation, and interval notation would have looked like this. Union negative 3 up to 3, union 3 to infinity. First of all, that's a lot of writing. Secondly, it's not quite as apparent where you have your discontinuity. Granted, yes, there's very physical breaks in the interval. Like you can see very clear breaks, sorry, in the intervals. So you can see where they are. But still, it doesn't, to me anyway, it's a little bit busy. There's a lot going on there. So I'm just going to get rid of that. Now what we can do is we can take a look at our domain and we can annotate each element that's excluded. We can talk about what they are. So like, is it a vertical asymptote? Is it a hole? So now we've stated the domain, and now we're going to look over at the original, and we're going to determine, can this be reduced? And it cannot. This is in its most simplified form. So we're going to leave that as it is. And then what that means is that everything that's undefined, both of these elements here, negative 3 and 3, vertical asymptotes. Okay, and so you would say vertical asymptotes. Usually most people just say VA, so you don't feel like writing vertical asymptote out. Vertical asymptote, x equals negative 3, x equals 3. Those are the equations of the vertical asymptotes. Remember, the vertical asymptote is not literally part of the graph. It's actually the not part of the graph. It's representing what you're not allowed to plug in. So you get this physical boundary. It's like you can literally see a dotted line that says, this is a fence, you cannot cross it because there are no x values there to plug in to get a returning y value. Okay, so there you go. That's one way to find vertical asymptotes. Vertical asymptotes are restrictions on your domain. Okay, the thing is, they're not always the restriction of your domain, as you're going to see in the next example. All right. So example 2 here tells us to look at our our function, and we're going to do the same thing again. We're going to factor the numerator, we're going to factor the denominator, and we're going to see what's happening after that. So yeah, my numerator, I like to just write on top of the problem like this, and then we can make it look neat in a second. So the numerator just factors into x times x plus 3. The denominator factors into x, 3, 2, plus, minus. And I believe that's right, x squared. Minus 2x plus 3x is positive x minus 6. Again, it's important that you check your work here. I feel like with that minus 6, sometimes you get other factors that could happen. Anyway, so yeah, we may as well rewrite the function. We're not simplifying here at all. I think some of you are like, but look, the x plus 3. Yes, true. X plus 3. X minus 2. All right, next, state the domain. So the domain, how about you pause the video at this point? Why don't you state the domain and see if you can finish this problem, predict what's happening. If you can't, still pause the video and state the domain, and then come on back. It's all x such that x cannot be, oh, I never finished writing this, silly. All right, x cannot be negative 3, and it cannot be 2. Great. So now that we've recorded the domain, we've recorded everything that could possibly go wrong with this function, right? We know that if x equals negative 3, denominator 0, undefined. If x equals 2, denominator 0, undefined. Now if you look over here, you say, hey, wait, let's do this now. We have x plus 3 cancels out, and we're left with x plus, f of x is equal to x over x minus 2. That x plus 3 that just became eliminated makes it so that negative 3 is defined. I can come over here and say f of negative 3, and that's going to be negative 3 over negative 3 minus 2, right? There's nothing wrong with that. So we're going to leave that there for a sec. So since that happened, it's really important that we identify in our domain the thing that's undefined. That's not a vertical asymptote. If something that was undefined in your domain becomes defined upon simplification, then that is what you would call a hole in the graph. You're going to graph that simplified function as if negative 3 is a value that we're allowed to plug in. That's just going to be something that we can do. So I'm going to annotate now over here. It's just really important to me that I state that we have a hole at, and I'm going to write the coordinate, negative 3, comma, and then you're like, wait, where do we get the y value from? You get the y value from evaluating f of negative 3. So we did f of negative 3 over here. That's what I started to do. So why don't we just bring that over to this spot and finish it up. And actually, I feel like just changing the color of that too to blue. All right. And that's going to be negative 3 over negative 5, which is positive 3/5. Great. So we have a hole at negative 3 comma 3/5 on our graph. And, you know, I don't know why I got rid of that. Well, I do. It's just kind of in the way. But I forgot that I could just do this. I use different blues too, if any of you are noticing that. Okay, so we have a hole at that point. Now that's not really that organized. I literally am writing right on top of my domain, but I really wanted to note to myself right there and then, I have a hole here, and this is super important that I don't like forget that later on. So, so we have that, and sometimes when you're graphing these, you might want to also state that elsewhere. So we're going to have vertical asymptote. There's only one vertical asymptote. That's at x equals 2, and then we have a hole at x, well, at the coordinate negative 3 comma 3/5. All right, so hopefully that clarified any confusion you had about the difference between a hole and a vertical asymptote. In the future, I'll have some examples of literally graphing these, and I'll intentionally choose one where you get to have a hole. But in the meantime, I would suggest even taking this function, plugging it into a graphing calculator, or even a program like Desmos, and just graph the original function and look at that vertical asymptote you found and that hole that you found and determine, like, does that make sense? Does it look like that would be there? Because that hole should literally be on the graph. It should look like it's just a point. They're not going to put the hole there. They're not going to demonstrate it, but it should appear to be part of your graph. All right. Thanks for tuning in.